Welcome. In this video we talk about smart pointers. There's lots of different types of them, and we will look at the most important ones. They integrate well with the type system and play an important role in what is called fearless concurrency, the fact that the compiler helps you to avoid a lot of common problems in concurrent code. First, we look at box. Box is a type which is available without including anything, and you create a boxed type just like this. Here we have a person struct, which is derived from by debug, and so we can print it. It has two public components, but that doesn't play a role here. Here, the box is simply a smart pointer which manages the allocation of one object. You cannot copy it, you can mutate it if the box is mutable, and you can access things in the box as if you had them directly on the stack. It's just a way to have the actual data on the heap and just have a pointer here on the stack. Therefore, the byte size of a box is always 8 on 64-bit machines. As you can see, here you see the changed value, and the byte size is 8. The second one is called RC, like reference counting. It's not yet for multi-threaded use, it's just for use in a single thread, and it lives in the module RC. You use it exactly as you would a box, and it's again just a pointer, but it keeps a reference count. You can clone it, therefore now C and B are pointers to the same piece of data, and then the reference count is 2. Once C is destroyed here again, it's back 1, and provided you have a RC pointer which has just one reference count, you can get a mutable access copy, so that's an option mut person, and provided you get access, then you can write to the data. Or if you don't get access, you get here a none, and then you don't get access. So if I run this here, I should get access because the reference count has been decreased here. So here it should be 1. So I should be able to set the age to 55. Let me run this. Indeed, it works. However, if I put this out of its scope, then C lives longer. And now this will always work, but I will now not get this here, but I should see the error message cannot get mutable reference because 2 references to the data object are active here. Let me run this. Indeed, I get 2 times the value 54, and I cannot get a mutable reference. So since I had 2 references to the same piece of data, the automatic reference counting made sure that I cannot get a mutable access here. Again, it's the usual rule. You can have multiple read-only accesses, immutable accesses, but only ever one mutable access. This is done here with an option type, but it's not thread safe, so you can only use this in a single thread. Very similar is the ARC, the atomic reference counted smart pointer. It's formed in exactly the same way as the RC. It's in the sync package, but it has the advantage that the reference counting is done with atomic values. That means you can have copies of an arc in different threads, and you can move them between threads. We will see this in the next video when we talk about the sync and send traits, that this has different properties. But for now it's behaved exactly like RC, since we have just a single thread. If I comment this one out here, I have just a single reference, therefore I can get a mutable copy. I get again an option type with mutable access. And if I run the program as such, I should be able to change the age to 55. Indeed, the age is 55. But if I comment this one out, then I have 2 references. And if I then try to get mutable access, it fails, cannot get mutable reference, and the age stays at 54. As you can see, the byte size is considerably larger. It's 40 on my machine here. The next smart pointer is a mutex. Mutexes in Rust are organized like a smart pointer, so you create a mutex by wrapping it around an object. Now, if you then you have a mutex with template parameter your type, and to be able to access the data behind the mutex, you have to lock it. Yeah? The result of such a lock operation is a typical result type. So either it's a mutex guard, that means you have the access to the mutex, to the data protected by the mutex, or it's a so-called poison error. We'll talk about this in a minute. So if you get access, you can access via this G variable here, which is unwrapped here to a type P person, mutex guard person. You can access it as if you had access to the data in the mutex. If you don't get it, this error message would be written. And likewise here, if this mutex guard goes out of scope, then we return the mutex. So that is, we cannot make the error to forget to release the mutex. Likewise here, we get it, we unwrap it, and then we have access to the protected data. Now, this is often seen because there's only one reason why the lock operation can go wrong. Namely, if another thread ran into a panic whilst holding the mutex. Then the mutex is so-called poisoned. And what happens if the mutex is poisoned? Then I get here an error result. I can either handle this here, or I can just unwrap, which means that this thread will also panic if the other thread has panicked. So that's a way to cascade the panic over to other threads. So therefore you quite often see that you just lock and unwrap and live with the fact that it will panic if another thread has panicked whilst holding the mutex. Let me run this. It works, I can change, and the byte size of the mutex object is 40. Very similar to a mutex is a read-write lock. This can be locked in two different ways, either for writing, then it's only one thread at a time which can get the lock. That's what I do here. So I do write, which gives me a guard here, and similarly to mutex, it can only fail if it's poisoned. And I can also lock it for reading. And it is just so that if multiple threads access the same read-write lock, they can get a read lock concurrently, and then you can access the data wrapped in the read-write lock from multiple threads. Let me run this. Exactly the same. This time the object has size 48. The next one is a ref cell. We are back in the single-threaded business. It's created as before. It's in the cell module here. You can get access by borrowing it, immutable access, and you can get write access by a mutable borrow. The difference is here that the usual rules, there's only one mutable borrow at a time or multiple shared immutable borrows, but this is computed at runtime. So it's a kind of reference counting to count how many references we have on this here. So this program will work as expected, and we'll see what the byte size of the ref cell is. Byte size is 40, and again I see the original value when I read it, and I see the changed value here. Here I change and see the changed value, and here I print the original value. The final one for this video is the cell. So that works its wonders in a different way. The access to the thing in the cell is granted only by changing the value. So the fundamental operation here is a replace operation. So you can replace the thing. The old object inside is discarded, and the next one is put in here. I think you can even get the old one out with this operation. And you can convert it into inner to something which is just on the stack. But then the object in the cell is empty and can no longer be accessed. So the mutability, the inside mutability of the cell comes just by being able to exchange and move out or in the value. Let me run this. 32 bytes. The exchange has happened. Notice that this is the only way to access things, and it's again only single-threaded. Time is fleeting. We are already at the end of this video. We have looked at various pointer types. We haven't covered everything. There's a once cell and similar things which just allow single operations, but you can read this up in the links in the document. For now, we leave it at that, but in the next video, I will introduce the copy, clone, sync, and send traits and explain in detail which of these pointers have which properties. This is very important to understand the fearless concurrency model of Rust. For now, see you in the next one.